Hello everyone, let's solve some Leetcode today. So today we have Leetcode 210, that is course schedule 2. This problem is very similar to course schedule 1. In the first problem, we were supposed to detect a cycle in the directed graph. If there was a cycle, we know that we cannot schedule or take all the courses and we return false. If there was no cycle, we simply return true. But in this question, we are supposed to give the ordering itself. So we have a number of courses that we would like to take that are labeled from 0 to n minus 1 or num courses minus 1. Then we have a prerequisites array. This array actually tells us which course depends on which other course. For example, here the A course depends on the B course. First you have to complete the B course, then only you can complete the A course. It means we have a dependency from A to B course. Now this relationship tells us that it's a graph problem because we can have some other course that depends on A. We can have some other course that also depends on A. So it becomes a graph where each course is actually a node in the graph. For example, here we have 0 and 1. First, I need to take the 1 course and then only I can take 0. So the order should be I take first 1 course and then I go to the 0th course. So it means the order will be 1 comma 0. So this should be answered, right? Now here the question officially asks us to give the ordering of the courses in which we need to take those courses to finish all the courses. It means there are cases where we might not be able to take all the courses. Let's take this example again. I have a 0th course that depends on one course to be completed. So it means I need to complete the one course first and then easily I can complete the 0th course, completing both the courses easily. What if there was also a dependency like this? 1 depends on 0 to be completed. That means I need to complete 0 before I complete 1. So now what? Which one do I complete first? And the answer is I cannot complete any of them because there is a cycle. So it means in the cases where there is a cycle in the graph, we know that we cannot complete all the courses. Yes, sure, we might be able to complete some parts of the graph where there is no cycle. But if you are talking about all the courses, complete graph, then if there is even a single cycle in the graph, we cannot take all the courses. Simple. Here is another test case in which we have to complete the 0th course first and then only we can complete the 1 course. It means the order in which we should complete the courses is 0, comma 1. This should be our answer and that is exactly the output. The main goal of this problem is to teach you how to find topological sort. Topological sort is simply an ordering in which if there is an edge between two nodes from U to V, in that ordering the V must always come before U like this. So what we are saying is that if there is a graph and U depends on V, then in the ordering of topological sort, write V before U, telling that you need to complete V, then only you can complete U. This helps a lot in build system. In big companies, you have many components, component 1, component 2, component 3, component 4, and they can have interdependencies. One depend on other depend on one, this one might again depend on this one. So we can have a lot of dependencies in the system, and there we need to find a topological sort to understand which component needs to be built first so that other component can be built. That's where the topological sort is usually used. Now there are two ways to find the topological sort. One is DFS and the other one is BFS. BFS means Kahn's algorithm. BFS or Kahn's algorithm is what we discussed in the course schedule 1 problem. So we can go for DFS in this problem. Now, yes, we are going to perform DFS on this graph, but understand that we also need to detect cycle in the graph. If there is a cycle, we are simply supposed to return empty array. That's it. As we already discussed that if there is a cycle in the graph, then we know there is no valid topological sorting. We cannot create any topological sorting for that. So we need a mechanism through which we can detect if there is a cycle or not. And that's where you need the knowledge of how to detect the cycles in directed graphs. So in directed graphs, we have two concepts, that is cycle array and visited array. In visited array, you store all the nodes that have been visited, just like in a normal DFS algorithm. In cycle, you actually store the nodes that are currently visited on the path of DFS that we are taking. Let's start the DFS now and we will understand on the go. So first I'm starting from the 1. So 1 is going to be in the cycle because 1 is on the current path of DFS. Now I go to the 2. 2 now is on the current path of the DFS, so I will simply add 2 here. Now I have a choice. I can go to 3 or I can go to 6. Suppose I go to 3. Now I have 3 on the current path, so I will simply add it on cycle. Now I will simply go to 4, so I will add 4 also in my cycle. Now I have a choice. I can go to 6 or I can go to 5. Suppose I go to 5. Now I will simply add 5 in my cycle. Simple. Now from 5, there are no outgoing edges. It means that 5 does not really depend on any other course. 5 is like an independent course that you can take by itself. So I will have an output array that will define the topological sort. So once we found a course that does not have any outgoing edges, or we have already traversed through all the outgoing edges of that node, we will simply put it in the topological sort array. So at this point, 5 is the course that we can take by itself. Now we will simply return. And when we are returning, what we are going to do is we will remove it from the cycle, because now 5 is not on the path of DFS traversal. We have already done it. And since we are returning, we have already gone through the 5 also, right? So 5 is what we will put in the visited set. So at this point, we are starting to fill up our visited. Now we are on the 4, and there is still one edge from 4 to 6 that we can take. So we will go from 4 to 6. We will simply add 6 in our cycle. And here in the 6, we can see that there is no outgoing edge. There are two incoming, but there are no outgoing edge. It means that we can take 6 by itself. So we are going to put 6 in our topological sort. And with that, the 6th node is also done. Now we will go back. And while we are going back, we will simply remove 6 from our cycle and we will put 6 in our visited array. It means that we have visited the 6 and we are not supposed to visit it ever again during any DFS traversal. Now we are on the 4th, and we can see on the 4th that we have gone through both the outgoing edges of this 4. It means we have completed all the courses that we require to complete before completing 4th. It means we can actually complete the 4th course now, so we will simply put it in our topological sort array. And now we can go back from 4th to 3. Now while we are going back, we will cross it, or we will remove it from the cycle set, because 4 is no longer on the path of DFS traversal that we are going to take. And since we have completed the 4th course, we will put it in the visited set and we will not go through it ever again. So here we are on 3, and 3 does not have any more outgoing edges. It had only one that goes to 4, and we have completed all the courses till 4. It means we have completed all the dependencies of 3. It means now we can also take the 3rd course. So I will put it in my topological sort, and we can now go back from 3 to 2. And while we are going back, we will simply remove it from the cycle because it is no longer on the path, and we will put it in the visited set. Now here on the 2, we still have an edge from 2 to 6. That means we still have a dependency from 2 to 6. It means that 6 needs to be completed before 2. So I try to go from 2 to 6, and we see that 6 is already visited. So we don't have to visit it again. It means we have already completed the dependency. It means we don't really need to go here. So we can simply place the 2 in our topological sort because we know we have completed all the dependencies of 2. So we can complete the 2 course now. Now we can go back from 2 to 1, and while we are going back, we will remove 2 from the cycle and we will add it in the visited. And now on the 1, we again don't have any more dependencies or any more outgoing edges. So we will simply add it in the topological sort here. And if we go back now, we are simply terminating our DFS call. So we will simply remove 1 from the cycle and we will put it in the visited. Now here you have your answer, the topo sort. This is what you can return at this point. This is going to be the answer. Now this was the happy path where we did not have any cycle in the graph, so we could easily figure out a topological sorting and we can return it. But what if? What if there was actually a cycle? So suppose I remove this particular edge and I actually create a cycle from 6 to 2. Let's completely have a new cycle and we will understand how the cycle and visited array will behave now. Now let us understand how the code flow will work. We will be on the first node starting from here. Then we will put it in the cycle. We will go to 2. Then we will put that into the cycle. Then we will go to the 3. That will be in the cycle. We will go to the 4th. That will be in the cycle. Now here we have a choice. We can go to the 5 or we can go to the 6. We will go to the 5. We will put that in the cycle. Now 5 does not have any outgoing edges, so it means that it is actually a part of topological sort. So we will have an array here. We will put 5 as a topological sort. Now we will go back from 5 to 4, removing 5 from the cycle, and we will put this in the visited. We will not visit 5 ever again. Now we are on the 4th node and we still have an edge to 6. So we will go to 6 from 4th now, and we will put the 6 in the cycle. And 6 itself have a dependency on other cores. There is an outgoing edge from 6 to 2. So 6 will try to go to 2, and we see that okay, 2 already exists in the cycle. It means that we found a cycle, that we cannot really create any valid or correct topological sort for this graph. And if we cannot create any correct topological sort for this graph, we know that we can only return an empty array. This is going to be the answer, an empty array. Simple as that. It's really, really, really simple. Now let us go through the code also. First of all, we are creating an adjacency list here as we usually do in the normal DFS traversal for graphs. Here on the basis of prerequisites, we are filling the adjacency list. Here we are deciding which node connects to which other nodes. Here we have the cycle and visited set declared, and this is the output array in which we will store the topological sort. And here is our DFS function. We will start from a particular source node. You can also call it course if you want, but source node is what I understand better. So we will start from a source node or a course, and if that node actually exists in this cycle array, then we know that it is actually a cycle and we have to return false. We cannot create topological sort for this particular graph. We will simply return false. But if it is not in the cycle and it is in the visited, now remember that we never remove nodes from the visited. Once they are visited and in the visited array, we don't remove them because we know that we are not going to ever go through those nodes again. So we need to remember that we have visited them. The cycle array is just for a path. You will be adding and removing elements in the cycle array based on the path you are going to take. So here, in case we have already visited the node, we will simply return true. If both of these base cases are not hit, we know that we have found a course or a node that is new. So we will add it in the cycle set, and then we will go through all the nodes that connect to this particular source node. So for all the nodes that connect to this particular source node, we will perform DFS on those nodes. If the DFS return false, we know that we found a cycle and we simply have to return false. We cannot create a topological sort. Otherwise, don't do anything. Take the next node and perform DFS on the next node. Here at the end, I'm removing the source node from the cycle because I know that it does not need to be in the cycle because I'm going back. And while I'm going back, I'm adding this into the visited so that I do not go through this node again. And also here, I'm appending this source node or this course into the output array because we know that by now we have completed all the dependencies of this node. So we can complete this node also. Now here is a tricky part. As we know that in a graph, we don't have to have all the nodes connected with each other. We can have isolated nodes also, isolated components themselves also. So for that reason, I'm basically making sure that I'm placing DFS call on every component that I can find. So I'm taking a course from the known courses, I'm applying the DFS on that course, and I'm going through that component. Now, in case after going through the component, if there is some isolated node that have not been visited, we will then be able to apply DFS on that also because of this loop. Now, if at a point we found a component in the graph that actually does have a cycle, we know that we cannot create a topological sort for the entire graph, so we will simply return empty array. Otherwise, if this entire thing passes, we know that our output array now contains a topological sort, so we will simply return that. Now let us run it and see what happens. So here we can see it takes 3 milliseconds and beats 77% of the solutions on Leetcode. This is a pretty efficient solution. Now let us talk about the time complexities and space complexities for this solution. The time complexity for this solution is order of V plus E. This is the number of courses and this is the number of prerequisites. And it is because we know that we have to traverse through all the nodes or all the courses, and we may do it based on the number of edges. We can have multiple edges from one node to many other nodes or many other nodes to one node. So E also becomes a component here. In the same way, we have space complexity as order of V plus E because we will have an adjacency list to store the graph. Now this adjacency list will take all the number of nodes and it will also store the relationship between them, so edges. So we will have order of V plus E space complexity for this adjacency list. We are not talking about the output array because it will take less space than this space. So we are going to take the upper bound. So yeah, like the video, subscribe the channel if you enjoyed it, and if you have some kind of question that you would like me to target or you have some kind of topic that you would like me to talk about, then just let me know in the comments. Now we will meet in the next video. Till then, bye.